Hi, Marina.
Hi,
How are you doing?
good and you?
Good. Just got back into town. Wow, I left and it was snowing, and I came back and it's snowing. What's with this ridiculous weather here? Um, I got this page here. I'm not giving an option to download it. I guess I don't need to. I can read it.
Do you have another page? I can take a picture. The same page.
This will work.
Can you read it?
Yeah, I can, and that's all that's necessary. Normally when I get an image, it gives me an option to download it, and that allows me to blow it up or shrink it or rotate it, any of those things. And this one does not give me that option. But I don't need that option on this one. So we can work with this.
I love you.
Okay, graph the function. Describe the domain and range. Compare the graph to the graph of y equals x squared. Okay. Let's shrink this a little bit. Put this under it. Whoops. Went the wrong way. Hold on. All right. This first one. Got my camera turned off because everything seems to be in slow motion tonight. So it was giving me I might experience audio difficulties with my camera on, so I turned it off.
Okay.
Okay. They want us to graph this, compare the graph to y equal x squared. Well, there's numerous ways to graph this, and I'm not exactly sure which methods they've taught you or what they want you to use here. Do you know?
No, I was gone Friday, so I didn't get to learn
Okay.
this.
There's a couple of ways to do this. Let's go over a couple of them. Do you know where the vertex is? Well, first of all, what kind of graph is this? What's y equal x squared? If we compare it to the graph y equal x squared, what does y equal x squared look like? What's it called?
Linear?
It's a parabola. If I was
Oh yeah,
plotting
I knew.
if I was plotting y equal x squared, that's what it would look like, just like that, okay? So that's y equal x squared. The most important part of a parabola is its vertex. And its vertex is this part right here. Because if you know where the vertex of a parabola is, you know the most important part of it. So there is a formula for figuring out the vertex of any quadratic. You know what it is? First of all, tell me if you've had this. Does this sound familiar?
Oh yeah.
Okay. Now, this is not really the vertex. What this is the x-coordinate of the vertex. Or, if you're going to plot a parabola, the line of symmetry, which would be the vertical line that goes through the vertex. Okay? So that's what minus b over 2a gives us, is the x-coordinate of the vertex, or it gives us the line that runs down through the vertex. So what is A and what is B? This particular
Negative
equation.
6 over 2
Well, first of all, what is A? Yeah, A is 3. What is B?
6.
No, it's this whole thing.
Negative 6.
-6. So now, what is negative B over 2A?
Positive 6 over 2 times 3.
Which is 6. So the vertex equals 1. Which means that if I draw a parabola, I'm going to draw my line of symmetry through 1, and the vertex is going to be somewhere on here. Don't know where yet. Could be any of these places, but I know it's going to go through that line of symmetry. Now, to figure out the y-coordinate of the vertex, plug in the x-coordinate into the equation and solve for y. So what happens when I do that? If I've got y equals 3x squared minus 6x, and I plug in 1 for x, what am I left with?
Could be y equals 3 times 1 squared minus 6 times 1.
What is that answer?
-3.
Good. So we have an x-coordinate on the vertex of 1 and a y-coordinate of -3. And that's the best way to get those, is to solve for the x-coordinate using minus b over 2a, and then solve for the y-coordinate substituting that x-coordinate into the equation. So our graph looks something, at this point, the only thing we know about our graph is that it's going to have a vertex at 1 comma -3. Well, this is 1. This is -3, so there's 1 comma -3. And we know it's going to go up. Now, the next thing we could use is some x-coordinates, or x-intercepts rather. In other words, if I have y equals 3x squared minus 6x, the next most important thing besides the vertex, because the vertex doesn't tell me everything. It doesn't tell me how skinny or fat this parabola is. In other words, it could be a parabola that goes like this, or it could be a parabola that goes like this, or it could be a parabola that goes like this. So I've got to figure out which. And what's going to tell me the best is either a y-coordinate, a y-intercept, or the x-intercepts. How do you solve for the y-intercept? Let's do the easy one. In other words, this parabola, where does it cross the y-axis? And how do I figure it out?
Substituting x as 0.
Good. What is y when x is 0?
Zero.
Right. So the point 0 comma 0, that has to be on my parabola. And that actually tells me everything I need to know, because I know that there is symmetry. In other words, if I draw this line of symmetry through the vertex, I know that it looks the same on the left side of that line as it does on the right. So if I know my parabola looks something like this, I know it has to be symmetrical on the right side. So this point right here, what is that? What are the coordinates on that point?
1, 1. Or I mean 2, 0.
2, 0. Very good. Because you know it has to be 1 unit to the right of that line of symmetry, because the other point was 1 unit to the left of it. And so that's actually all I need to know to graph it. Now, there's various ways to do this. There's like 3 different ways to figure out how to graph this. And I'm not sure which one she has focused on in class. Have you talked about completing the squares?
Yeah.
Okay, let's do it that way. If we have y equal 3x squared minus 6x, the other way we can figure out how to graph that function is by completing the squares and putting it into y equal a times x minus h squared plus k, which is vertex format. If I can get this function into y equals a times x minus h quantity squared plus k, then h and k are the vertex. So if I complete the square on this thing, I get the vertex without having to go through the minus b over 2a.
I thought completing the square was negative b plus or minus the square root of b squared minus 4ac over 2a.
That's the quadratic formula.
Oh, we learned the quadratic formula, but I don't know if we learned the one that you just said.
Completing the square? Okay.
Oh, never mind. Yeah, we learned that.
Let me go through how we would complete the square on this. First of all, we're trying to complete the square on this part of it right here. I'm going to set it equal to 0. Okay? That's how we're going to do it. Is we're going to take the function, set it equal to 0, and complete the square. Now remember, the first time through we got x equal 1, y equals minus 3 were the vertex. Well, this is going to give us the vertex also, just a different method. Now, in order to complete the square, what's the first thing you have to do to the term that is squared, this x squared? What do we need to do in order to complete the square? We can't do it as long as there's a 3 in front of that. We can only complete the square if there's a 1 in front of the x squared term. So we factor out a 3. So the next step is 3 times x squared minus 2x. Notice that I haven't changed it. That and that are the same thing.
Then plus 1.
Okay, now I'm going to add plus 1 to the left side of the equation. What do I have to do to the right side of the equation to balance things?
Add 1.
How many did I really add to the left side of the equation? I wrote in a 1, but how much did I really add to this whole left side?
Oh, 3?
Yeah, because it's all being multiplied by that 3. So really to balance it, I have to add a 3 over there. Okay? So now I have it as 3 times, and the whole point of completing the square is so I can write this as what? How can I rewrite this? Remember, what I'm looking for is an x minus h quantity squared. So it would be x minus what squared?
1.
Yes, good. That's equal to 3. And now I'm going to move the 3 onto the other side so that I get 3 times x minus 1 squared minus 3 equals 0, or y. Remember, I started with y, so I'm going to resubstitute the y there. And now I have it in the format that's called vertex format, which is this. if I can get the function into this format, then the vertex is located at h comma k. Well, in this particular function, after I completed the square, what's h?
1,
And what's k?
3.
Minus 3. Remember, this is a plus k. So the fact that I have minus 3 here means that k is minus 3.
Okay.
And I get the same thing that I got by doing it the other way. I got 1 and minus 3. So either method allows me to graph it. And which one you use doesn't really matter. It just kind of depends on what are you working on in your class at the moment. Are you working on completing the square and getting it into the vertex format? Or are you looking at the finding the vertex from minus b over 2a?
We already did the vertex part, so we're doing more of completing the square and the quadratic formula.
Okay, well this doesn't require the quadratic formula, at least yet, because that is yet a third way of solving for it. But I don't want to go over that because we won't get to any of the other problems. But it is important for me to know which one you're doing. It sounds like you're completing the square on these and getting it into the vertex format. In the vertex format, what's A for this equation?
3.
Correct. A is 3, H is 1, and K is minus 3. All right, so let's see, one other thing they wanted here was describe the domain and range. So if we look at this part of it, the very last line here, tell me what the domain is. What does domain mean?
Usually it's like the x-intercepts.
No. Domain means what are all of the possible values that x can attain here? Can x be 10?
No?
Yeah, sure it could. We can substitute anything we want for x. X can be negative infinity, x can be 0, x can be positive infinity. Let's talk about domain for a second. What's the domain of this function? What can x not be? Usually when you're asking about domain, the thing you want to look for is what can x not be? Well, the one I wrote and circled, what can x not be there?
1.
No? If x is 1, y is 1. X can be minus a billion, x can be plus a billion. But there is one number that x cannot be.
0?
Yeah, you cannot divide by 0. You can look up anywhere on the internet and look for 10 commandments of math. They'll all be different, but they all have the same first commandment. Thou shalt not divide by 0. Never forget that. You can never, ever divide by 0 because you get infinity if you do. So usually that is what gives you a restriction on what x can be, is when it's in the denominator. Or if I'm taking the square root of it, it's got to be positive or 0. In other words, this cannot be negative. So if I was asked about the domain of this, I would say, well, all numbers greater than or equal to 0. So domain is whatever x can be allowed to be. And in this function here, there are no restrictions. I can let x be anything I want. Okay?
Oh, I get it.
So the domain, do they make you give it an interval notation? Like that?
No.
Or they could say all reals. The domain is all real values for x. X can be anything.
Yeah, it can be all real values.
Now let's talk about range. Range applies to y. Range is all of the possible values that y can be. Well, let's start with a simple one before we look at this one. What if I said y equal x? No, excuse me. Let's say y equals square root of x. Let's talk about this function right here. What can x be again?
All real numbers.
No, we're talking about this new function. I want to talk about range for a second. And in order to talk about range, I want to start with an easier problem. So if I talk about y equals square root of x, the domain, x has to be only 0 or positive numbers. You can't take the square root of negative numbers. So the domain of this function would be x greater than or equal to 0. What's the range of this second function here? What are all the possible values that y can attain? Can y be negative?
Yeah.
How do you get a negative y? What value for x would give you a negative y? You cannot get a negative y because you can only use positive values for x or 0, and when you do that you only get positive values for y. So the range on this function would also be y has to be greater than or equal to 0. You can take the square root of 0 and get 0, but you cannot take the square root of negative 1. In other words, and whenever you take the square root of positive values, you always get a positive value. So on a function like this, it's a good illustration of what domain and range mean. The domain is what x can be. The range is all of the possible values that y can be. Okay, you with me?
Kinda.
Well, where are you confused?
About the whole range.
Okay, let's do some other easy ones. This one's a little tougher, so before we get to that one, I want to make sure you understand range. What if I said y is equal to 1 over x? Let's talk about this function. What can x be? Or better yet, what can x not be? Because it's usually easier to figure out what x can't be than what it can be. What can x not be?
0.
Okay, so it can be any other thing except 0. It can be minus a billion, it can be minus infinity, it can be plus infinity, it can be plus a billion. It just can't be 0. Okay, so what can y be in this one here? Can y be negative?
No.
Yes. If x is negative, y is negative. In other words, if I say y equals 1 over a negative 10, if I make x minus 10, then y is equal to minus 1/10. So it's easy enough to make y negative. Can y be positive? We're talking about this one right here. Can I figure out some value of x that makes y positive?
You froze, so I didn't hear anything you said.
Can I make y positive in this function that I've circled here? Can you hear me, Marina?
Yeah.
Okay.
What'd you ask?
I said, can I make y positive? Can y be positive?
Yeah, if x is positive.
Sure. So y can be negative. Y can be positive. Can y be negative infinity?
Yeah.
Yeah, if I make x extremely tiny. Notice what happens to y as I play with x. What happens if I make x 0.1? Then y becomes 10. What happens
Wow.
if I make x 0.01? Then y becomes 100. And if I make x 0.001, in other words, as I make x smaller and smaller and smaller and smaller, y gets bigger and bigger and bigger and bigger. So y can actually go to infinity as x approaches 0. You see that?
Uh-huh.
Well, as x, if I make x negative that number, then y actually approaches negative infinity. So y can go to negative infinity, and it can go up to positive infinity. But there is one number that y can never be. That there's no value for x that results in this one number for y. What would that be, you suppose? What can I not get y to be?
0?
Yes. It can never be 0. No matter what I do with x, I can let x be 1,000,000,000, and y is still not 0. The only thing that can possibly make y 0 is if the numerator is 0, and our numerator is fixed at 1. So y cannot be 0. So the range on this function is, we already figured it could go to negative infinity, but it can't be 0. So it's that combined with this. Now, you're saying this notation does not look familiar?
No.
This is called interval notation, and it's difficult to talk about domain and range without interval notation. Now, one way she might be saying the same thing is that the range can be all real numbers except 0. Except 0. So she might have you write it like this. So with this particular function, x can never be 0 and y can never be 0. So the domain and range for this are pretty much the same thing. All real numbers except 0. Okay?
Okay.
All right. Now we're going to go back and look at the problem that you have. What are the restrictions on x? What can x be?
Any real number?
All reals. There's no value for x that presents any problems. In other words, there's no value of x that causes us to divide by 0 or take the square root of a negative number or any of those things we're not supposed to do. So the domain is all reals. What's the range? Let's take a slightly easier one. Let's take the parent function that they gave us. Let's talk about this. What's the domain on this?
Anything but 0?
Actually, it can be 0. There's nothing wrong with making x 0. You can square 0. You just can't divide by it. Okay? So y equal x squared has a domain also all reals. What's the range of this y equal x squared? Can you make y negative?
Yeah.
How? Tell me what value of x would make y negative.
Oh, no, you can't, because a negative times negative equals a positive.
Which means y is always going to be positive except when x is 0. And then it'll be 0. So the range is all y's greater than or equal to 0. So here's a function where the domain is all reals, but the range is only positive numbers. Okay?
Okay.
Now we're ready to talk about this function here. And it's very important that you remember that the range is only positive numbers when you're looking at this kind of a situation. Okay, well, we've already figured out that the domain is all reals here. What's the range going to be?
I'm still confused about how to find the range.
Okay, let's plot it. Maybe that'll help. We plotted it the first time, and it plotted at the vertex there. If I give you the graph, can you see that the domain is whatever x wants to be? And that actually, even though it's not obvious from this graph, but x can only go from negative infinity to positive infinity. Can you read the range off the graph? What are all possible values of y?
From 0 to infinity.
Well, I'm looking at a y here that's minus 3.
Negative infinity to positive infinity.
I don't see any y's less than minus 3. Remember, when we're trying to figure out the range, we're looking for the y values, not the x values. The y values. Well, the lowest y value I see here is minus 3. What's the highest y value you can get?
Infinity.
Okay, so the range is y has to be greater than or equal to minus 3. There's your range right there. Now, it's easy enough to see that from the graph, but we can also see it from this equation, because I know that this part of the equation can at best be 0. There's no way this part can ever be negative, right? Because x minus 1 squared has to be a positive number. So even if I made x 1, I've got 3 times 0. In other words, this can never be negative. The lowest this can ever be is 0. And if that's 0, then I've got 0 minus 3, so y could be minus 3. But it can never be minus 4. How would we ever get it to be minus 4? For y to ever get to minus 4, this part of it would have to be minus 1. And we already know that there's no way to make it minus 1. When we square a number, it always is positive. So you don't necessarily have to graph it in order to see the range. you can look at this algebraic function here and determine that the range has to be from -3 to infinity. But maybe at this point in algebra, they're wanting you to figure out domain and range after you graph it. And that's why these questions say, graph it, then give me the domain and range, and then compare the graph to y = x squared. Okay?
Okay.
So we've given the domain and range. Now let's talk about what kind of translation or transformation our graph is from the parent function, y = x squared. Well, if you'll remember, our graph was like this. This is y = 3 times x minus 1 squared minus 3. Well, you've had translations, correct? You know what it means to translate a function to the left or right, or up and down? What's that?
To move it, like...
Yeah, so how does this compare with the parent function? Has it been moved right or left?
The dotted or solid line?
The dotted compared to the solid. In other words, we're comparing this function they gave you with the parent function.
It moved down and to the right.
Well, it moves to the right 1 and down 3. And it moves to the right 1 based on this, and it moves
down 3 because of -3
based on that. And it does one other thing based on this 3 here, and that's that it gets 3 times as skinny. In other words, the original parent function is wider, notice, than our function. Our function is 3 times as steep. Let me give you a better example. If I graphed y = x squared, this is y = x squared. And if I said, what's the graph of y = 3x squared? Well, this 3 does what? It's a vertical stretch, which on parabolas makes it skinnier by a factor of 3. So the vertical stretch would cause this thing to look like that. In other words, that is that function. Understand?
Yeah.
Okay. There's one other thing let's talk about while we're talking about it. If this number, this coefficient in front of the x squared is a number less than 1, like 1/2, it makes the parabola fatter.
Because it's smaller?
Because it's less than 1. If that vertical stretch factor is between 0 and 1, it fattens the parabola. If it's greater than 1, it makes it skinnier.
Oh, okay.
It's an important thing to remember. So when we looked at this function that they gave us, we had a vertical stretch factor of 3. So it's not going to be the same width as this original parabola. It's going to be 3 times as skinny. In other words, so all of the things taking place here are horizontally moving to the right by 1, vertically moving down by 3, and vertically stretching it by a factor of 3. And that's how we get that. And we've answered everything they want to know about that first question. All right?
All right.
All right, let's do another one. Now, we took quite a bit of time to do that. But each one of these are different enough that we need to do all of them. So let's look at number 2, because each one of these are parabolas, but there's just enough different about them that we need to keep going. So let's solve this one also by completing the square, not by finding the vertex. And in this one, I'm going to move that 17 over to the left, to a minus 17. I'm going to say that's all equal to y. You with me? On what excuse me, that's a plus 17, my fault. In other words, I didn't move it to any other side of the equation. It was on this side of the equation to begin with.
Okay.
Okay. Now, in order to complete the square, what's the first step I got to do?
Subtract 17.
That's what I did on the last one, but that really wasn't the way to do it. I made kind of a mistake there. I probably gave you a false impression. When we're completing the square, we want to work with this part only. And I don't really need to take that 17 to the other side. Here, I'm going to show you what I'm going to do. I'm going to complete the square with just the terms with x. And I'm going to leave the 17 on the same side of the equation. And this is all equal to y. And remember, I want to get this, what's the general format, the vertex format for a parabola? It's y equal what?
Negative b over 2a.
Well, that's the vertex. That's to find the vertex. But if I want to put it into the vertex format, I got to get it into this format right here. If I can get my function into this format, then I will know where the vertex is. The vertex will be at h and k. Let me write this right above so you'll know what we're doing. Now, the secret, what's that? This is called the vertex format for a parabola or a quadratic right here. I want to get it so that it looks like y equals a times x minus some number, all squared, plus k. If I can make this look like that, then I will have it in vertex format, and I'll know where the vertex is.
Okay.
So in order to do that, I got to complete the square. If we're going to take an expression like this, and be able to write it as an x minus h quantity squared, then I have to complete the square to do it. Okay? So what's the first step in completing the square? Getting rid of that coefficient.
Is the coefficient negative 24x or 17?
Not the 24, the coefficient that's in front of the x squared term. These are coefficients. This is not a coefficient here. That's a constant. Okay? I do have a coefficient in front of the x squared, and I have a coefficient in front of the x also. But the one that I have to make equal to 1 is the one that's in front of the x squared. So if I factor out a negative 6 from that, I get minus 6 times x squared minus 4x. Actually, x squared plus 4x. Correct? Still have this plus 17 over here. In other words, the secret about completing the square is you never change the equation. I haven't changed anything. If you distribute this negative 6, you'll get back to where we started from. But the reason I factored out a negative 6 is because now I have a 1 in front of my x squared, and I can complete the square. How do I complete the square on this thing? Starting from here.
Um, Adding 4 to both sides.
Okay. I definitely want to add a 4 right there, but when I add a 4 to that, what have I really done to this left side of the equation?
Oh yeah, added a 24.
I've really subtracted 24. In other words, minus 6 times that 4 is a negative 24. So the moment I wrote in a 4 there, I've subtracted 24 from the left side of the equation. Now, when we did it the first time, this 17 was on the other side of the equation, right? This time,
No, 17.
no, and when we did it the first time, I put that.
Oh.
This time I'm going to leave the 17 on the left side of the equation. But I've just subtracted 24 from the left side of the equation. So to balance it out, I got to add 24. Now I haven't changed anything. In other words, by adding 24 to the left side of the equation, I merely balanced out the fact that I just subtract 24 from the left side of the equation. If I was doing something to the right side of the equation, I would have to subtract 24 to that. But I'm not. I didn't do anything to the right side of the equation. The right side of the equation is y. So everything I'm doing here, every change I'm making only to the left side of the equation. So when I went from this step here, number 1, to this step here, there's no difference between those two. Notice that as all I did was I subtracted 24 and I added 24 to the same side of the equation. That's a net 0. So now what I have is this. Y equal minus 6. And this part that's inside the parentheses I can now write as x plus 2 squared, which was my goal. That was why I completed the square, because when you complete the square, you always guarantee that you're going to be able to write it as x plus or minus some number squared. And then I still have this part, which is now plus 41. Notice that I now have it in perfect vertex format. Vertex format is once again y equal a times x minus h squared plus k, where h and k are my vertex. So with this particular equation, what is h? And what is
Positive
k?
2.
Well, is it a positive 2?
Oh, negative 2.
A negative 2, because then x minus a negative 2 would give you x plus 2. If it was x minus 2, h would be a positive 2. But in this case, h has to be negative for us to get this positive. What is k?
Okay.
What is k?
Positive 41.
Correct. So now I know how to graph the most important part of it, which is the vertex. I'm going to put the vertex. Let me graph it. I've got an h of negative 2, a k of 41. Let me do this again. So here's negative 2. Here's 41 up here. So I'm going to say there's my vertex. Coordinates on that vertex are minus 2, comma 41. Okay, you with me?
Mm-hmm.
Which way does this parabola go, up or down?
Up.
Remember,
Down.
goes down because that a is a negative number. This negative sign says that it goes down. when I graph that, the very first thing I look for after I found the vertex, I found the vertex, but I don't know if it goes up or down until I look at this negative sign. And then I see that it goes down. How much skinnier is it than a regular parabola? Six times.
Oh, because it's -6.
Yeah, so this thing's going to be really skinny like that. Okay, now I still haven't drawn it exactly. I've drawn a good estimate because I found the vertex. I know how skinny it's supposed to be, and I know which direction it's supposed to be. But to really adequately graph it, I need either a y-intercept or two x-intercepts, but I need two more points. So let's erase it again. I know the vertex is there. What's the easiest intercept to plot? Is it the y-intercept or the x-intercepts?
X?
Actually, the y. Why is that? Plug in x equals 0, and it's real easy to figure out what y is.
Oh, yeah.
And the y-intercept is always where x is equal to 0. The x-intercept is where y is equal to 0, and the y-intercept is where x is equal to 0. So plug in 0 for x here, and what do you get? For y. What is y of 0 equal to?
Do I plug it into...
The original function, right there.
Okay.
Plug in x equals 0. What's 2 squared?
39.
What's 2 squared?
4.
Okay, so we have minus 6 times a 4 plus 41. Minus 6 times 4 is minus 24 plus 41, that's 17.
Oh, I added the 4 to 41 before I multiplied it.
So there's that point right there. That's 0, 17. We know the graph has to go through that. So that's easier than finding the x-intercepts. And it also completely solves my problem because I know this thing is symmetrical. So I know that if this point is on it, and if I go 2 units to the other side, I got to be at 17 also, right? In other words, that point has to be minus 4, 17. And the graph has to look like this. Now, I still don't know the x-intercepts, but once you have 3 points on a parabola, you got enough to graph it. I'm not sure what your teacher is telling you. She may want 5 points, but 3 points is enough to graph a parabola. And with most quadratics, once you've found the vertex, if you find 1 point to the right or left, then you're really finding 2 points because you know it's symmetrical. In other words, I know this point right here is 2 units to the right. That means if I go 2 units to the left of that point, I'm also going to be at 17. So I don't really have to figure out this point. I can base it on symmetry. But I did have to figure out that point by finding the y-intercept. All right, now let's just, before we leave, it's 9 o'clock, but let's answer the rest of the question, which is, what's the domain? Read it from the graph. That's the x-axis. This is the y-axis. The domain is everything that x can possibly be. Is there any value you can figure by looking at that graph that x cannot be? Can x be minus a million? Look at this graph. Can x be minus a million? Yes. It doesn't look like it from this graph because the furthest to the left I see, I lost you, didn't I? Marina?